Good morning, champs. Today we solve a classic complex analysis task. We are given the real part of a holomorphic function, u of xy equals y over x squared plus y squared. And we want to reconstruct the full function, f of z equals u plus I times v, on the complex plane without zero. The key idea is this. If a function is holomorphic, then its real and imaginary parts satisfy the Cauchy-Riemann equations. That means u sub x equals v sub y and u sub y equals minus v sub x. So our plan is simple. First, compute the partial derivatives of u, then use the Cauchy-Riemann equations to recover v. We start with u of xy equals y over x squared plus y squared. Before differentiating, let's briefly recall the quotient rule. If we differentiate a fraction g over h, we get g prime times h minus g times h prime all over h squared. Now let's apply that. First, the derivative with respect to x. Here, y is treated as a constant, so we get u sub x equals minus 2xy over x squared plus y squared, all squared. Now the derivative with respect to y. Using the quotient rule, we get u sub y . So this simplifies to u sub y equals x squared minus y squared over x squared plus y squared, all squared. Now we use the first Cauchy-Riemann equation. Since u sub x equals v sub y, we have v sub y equals minus 2xy over x squared plus y squared, all squared. To find v, we integrate with respect to y. So v of xy equals the integral of minus 2xy over x squared plus y squared, all squared, with respect to y. To make this easier, we substitute w equals x squared plus y squared. Then dw equals 2y dy. So the integral becomes the integral of minus x over w squared dw. Integrating gives v of xy equals x over x squared plus y squared plus c of x. And this is important. Because we integrated with respect to y, the constant of integration may still depend on x. Now we determine c of x. Differentiate v with respect to x. V sub x equals minus x squared plus y squared over x squared plus y squared, all squared, plus c prime of x. But from the second Cauchy-Riemann equation, we know, and since u sub y equals x squared minus y squared over x squared plus y squared, all squared, this means v sub x must equal minus x squared plus y squared over x squared plus y squared, all squared. Comparing both expressions, we get c prime of x equals 0. So c of x is just a constant. For simplicity, we choose that constant to be 0. Therefore, v of xy equals x over x squared plus y squared. Now we combine real and imaginary parts. F of xy equals y over x squared plus y squared plus I times x over x squared plus y squared. Putting that over one denominator gives f of xy equals y plus ix over x squared plus y squared. Now let's rewrite this in complex notation. The symbol z bar means the complex conjugate of z. So if z equals x plus iy, then z bar equals x minus iy. Now notice, I times z bar equals I times x minus iy, which simplifies to ix plus y. So the numerator y plus ix can be written as I times z bar. That gives f of z equals I z bar over mod z squared. And now we use one standard identity. Z bar over mod z squared equals 1 over z, as long as z is not 0. So finally we obtain f of z equals I over z. That is the holomorphic function with the given real part. So this example shows something very powerful. If we know one part of a holomorphic function, the Cauchy-Riemann equations can determine the other part. That is one of the reasons complex analysis is so structured and so elegant.